Hey folks, in this screencast, we introduce our first model that deals with a dissipated force, and that's a friction model that we call Coulomb friction, also considered dry friction. And so this is something that we use often because we need to encounter and we need to accommodate for this energy loss that occurs in the machines that we design and that we analyze. And so you've probably seen this model before from physics, in which we have the friction force is equal to the proportion of which is defined by a constant coefficient of friction, and then the normal force. The Coulomb friction model has three assumptions that we have to take into consideration. The first is that the magnitude of friction is proportional to the normal force, and we see that because we have a coefficient of friction multiplied by the normal force. And the second is that it's independent of contact area. So notice here in this equation, it has nothing to do with the surface geometry. And then the third is that it's independent of speed. So it doesn't matter how fast the two objects are sliding with respect to each other, the force itself is independent of that. And the best way to do this is just work an example so we can apply this model to a real-world problem. So what we see here is a block sliding on a surface. There's a coefficient of friction between the block and the surface. The block has a mass m, and we want to find the equation of motion if given a boundary condition, an initial speed, for example. And we want to solve for the equation of motion and then solve the equation of motion that includes this friction force. And we start by defining our reference frame and then the coordinate that defines our kinematics. And in addition, we need to define the direction of gravity. So gravity is going down according to our drawing here because we're going to use that and we'll need that when we calculate the normal force. We'll obtain the equation of motion by inserting the elements into Newton's second law. And so we need to get the force on the left-hand side, so we draw a free body diagram. And on the free body diagram we include all the forces. So we have the force due to gravity, we have the normal force, and now the only other force that we have acting on the block is our friction force. Now here's where we have to ask the question of which direction do we draw our friction force. Now the block is sliding from the left to the right along the x-coordinate, and the friction is always going to be in the opposite direction of which it's sliding. So it's in the opposite direction of the velocity. So with our convention here, with our model, we always use a negative sign, but then this is where this term on the outside comes into play. So in this friction model, because we always use a negative sign, and we're going to correct with this term, we always draw our force, our friction force, in the direction of positive speed or positive velocity. And so here, x is pointed to the right, so as x increases, then it'll be moving to the right, so positive x dot is to the right, so our friction force will be placed in this direction. And so we insert this into Newton's second law, and on the left-hand side, the only force that we have acting in the direction that we're interested is the force F, sub F, and that's in the positive direction, and this is equal to the mass x double dot. And so F sub F, according to our model, is negative mu n, and then it's Vrail divided by the absolute value of Vrail. So let's figure out what's going on with this Vrail term. So the Vrail is the relative speed, and it's the relative speed of the object itself to the point of contact in which it's sliding. And so in our example, the V sub p, which is the point, is our block, and it's sliding according to x dot. So V sub p is x dot, and then the object that it's sliding against is the ground. So our contact point C, and you can even draw in a contact point C, has a speed of 0. So then when we insert them into our Vrail, so our relative speed, it's equal to x dot. Now this is an intuitive solution that you see here because we're saying that if this mass moves to the right, then its relative velocity to the contact point is going to be x dot. And where this model really shines is when you have two objects that are both moving and then moving against each other. Because if the ground were moving to the left and the block itself were moving to the right from our reference frame, that we would need to consider the relative velocity between the two objects. And so we insert Vrail is equal to x dot into our equation as we're developing our equation of motion. And now see what's happening here is that we have a corrective factor that's going to allow the direction of force to change if the direction of speed changes. So in this case, we're going to solve these equations for a positive speed, so with the block moving to the right. And so intuitively, if the block is moving to the right, then our force should point to the left, or should be negative in this circumstance. And we see that happening here. A positive speed divided by the absolute value of that speed gives us a coefficient of 1, and so we get that the friction force is to the left and resisting the motion as it moves to the right. And if we change that direction, where we get a negative speed and x dot becomes negative, it's then divided by the same scalar magnitude, but then retains the negative sign and cancels out this initial negative sign in our model. And so it points our friction force to the right to counteract a left movement of the block. And so now what we have here is a general application of the friction model in which it'll change direction of the force based on the direction of the motion automatically. In the vertical direction, we're maintaining static equilibrium, so the normal force is equal to mg, and we'll insert this into our equation and then solve for x double dot to get the equation of motion. To solve the equation of motion, we apply our boundary conditions at time 0. So we're saying that we start with an initial speed, x dot at time 0, and an initial position, x at time 0. And then we directly integrate our equation to x dot and then x. And so here with the solution of our state, we see that we begin with an initial speed, and then that's going to decrease at a linear rate until it equals 0. We then find the time t that it takes for the speed to become 0, and then apply that to our position equation that gives us our change in distance from the initial starting position to the final position. So in summary, we've introduced a friction model that automatically accounts for the change in direction. And this change in direction is taken care of by this relative speed between the point that's moving and the surface on which it's making contact. And then keep in mind these three assumptions of the friction model, that we're ignoring the actual magnitude of the speed, the contact area, and then we're making this really simple assumption that the friction force is always proportional to the normal force.